Hi there, I'm going to be talking through this paper, Prompt Waywardness, the curious case of discretized interpretation of continuous prompts. The idea here is to try and marry the two worlds of continuous and discrete prompts. So discrete prompts being like more prompt engineering, whereas those continuous prompts are going to be in the vein of Lester and Li and Liang, where they're perhaps randomly initializing, but training the actual parameters of those prompts to get somewhere. The question is, hey, we have these continuous prompts. What do they actually mean? If we were to map them to discrete prompts, what do they actually represent? And the paper here suggests that there's a waywardness to this mapping, where the representation of these continuous prompts in a discrete space, specifically evaluating these things as discrete spaces with respect to like word embeddings, that is not very clear in terms of what is actually represented. What they aim to do more specifically is look at these continuous representations, map them to discrete representations, and ask the question, do these mapped continuous representations map to things that are semantically meaningful to the text or to the task at hand, or are we mapping to perhaps arbitrary tokens? Let me get into this a little bit more. So they're asking the question, is it possible to come up with meaningful discrete interpretations of continuous prompts, especially ones that provide a faithful explanation of the prompt's behavior? That would be really awesome, right? So they're looking at nearest neighbor of discrete language representations, and their waywardness hypothesis, like I said, suggests that there is little correspondence between continuous prompts and their discrete interpretation. They're looking at 5 different classification data sets, and they specifically define this as being specific for classification. What they're looking for are prompts that project to a given discrete prompt with a token overlap of 94% F1, while scoring within 2% accuracy of the best continuous prompt-based solution for the task. What this means is that there's, continuous representations that don't really mean anything, but are still going to let you do pretty well in downstream tasks. They have some interesting findings with respect to model size and the length of prompts. They're going to look at some of the structural properties of language models that explain that. They get into some really fascinating stuff with some of the risks here, where we have models that we basically can't interpret, or perhaps interpret in the wrong way because we're saying that, this continuous prompt maps to this, but that might not actually be meaningful. They have some cool theorems further on. So let's talk about prompt waywardness. So what we're doing is we're developing a projection of this discrete prompt, as you can see here. You can define things that way, and then you can also understand that there is a discrete projection of a continuous prompt as well. So let's see here. Yeah, they talk about like how this is like a vocabulary selection sort of thing. They're specifically using some projections for these discrete to continuous to discrete models. They're pulled from GPT-2. I think that is a generally good idea, given GPT-2 works well and that sort of stuff. They can further define the loss. This P plus X is like the prompt plus the input. It's not actually adding those vectors together. It's like a concatenation. The waywardness hypothesis. One can easily verify that such continuous prompts are not unique, e.g. random initializations lead to different outcomes. Resultant prompts get projected to seemingly irrelevant discrete elements. That is basically what the waywardness hypothesis is. So they're going to use a couple of ways in which to structure this problem. So in this case, they're going to define a loss specifically for the continuous prompt, and this D is just like projection to whatever the data is saying, like a standard supervised learning objective, and then they're tacking on this gamma piece here, in which they're defining a distance between the continuous and discrete prompt, because we don't want to totally distort the similarities or lack thereof between the continuous and discrete prompt. Ideally, you have like a discrete prompt that is relatively close to your continuous prompt and vice versa. So yeah, the large value of gamma will make your continuous prompt even closer, possibly identical to that projection of the discrete prompt, but lead to poor accuracy in a target data set. So they use gamma equals 0.01. So yeah, I think I've explained like what the setup is for this in pretty good detail. They're going to also look at the F1 score here, as well as this like more standard loss, specifically for the like continuous distance and discrete distances. So let's get into some of the results. So this is like the first table that really matters. So what they're looking at here is this delta. This delta is sort of what the degradation is when you were setting gamma to 0 versus 0.01, saying that you want relatively close projections. So the idea is, okay, if we're remaining relatively close to whatever our continuous prompts are, then that should perhaps degrade performance like significantly, because we are, not tuning quite as much as we otherwise would if we were unconstrained. So the finding from this, though, is that we don't actually see that significant of degradations in performance. I would say on average, this is looking at like maybe 1%, some decimal point percent degradation in performance as you like change that objective. Furthermore, the F1 scores remain super high. So this suggests that, yeah, we can, one, remain relatively similar to our whatever the like optimal discrete prompts are, while not actually having significant degradations in accuracy, even though we're perhaps mapping to totally nonsensical things. So they look into some other pieces here, specifically like some ablation studies. So they look at prompt length, and actually, yeah, before I get into that, I just want to like sort of show what it is that they're actually doing. So that this example here is super illustrative. So you can imagine that so they have this discrete projected prompt of whatever the like optimal continuous prompt is, right? So in this case, and this last line in particular, we see that our like projection to discrete space of our continuous prompt is messy in like the football player. Our accuracy is degrading by like 0.4%, and that prompt F1 is still somewhat high, which is scary, because yeah, this means you can sort of find random, seemingly optimal continuous prompts that are not actually semantically meaningful. Similar thing going on here with our terrible sheep. That makes zero sense, right? This like first example is like whatever the optimal like representation would be. So as you can see, terrible seems to have a huge pull here on this other task as well in SST5. So this is really the core like representation of what is going on in this like sort of paper. Again, getting back to ablation sort of related things, so they look at prompt length. So when they have smaller prompt lengths, it's relatively difficult to learn a continuous prompt that is close to the discrete prompt. The prompt being too short significantly hurts the expressivity of the prompt. That makes sense, and that is shown here. As you can see, accuracy goes up as you lengthen your prompt. I think this is unsurprising. We're adding basically extra parameters into the model that give us quite a bit of flexibility in terms of how like many tunable parameters there are, right? The size of the model increasing here. I think this is perhaps more so a reflection of there being better capabilities with that larger prompt, or sorry, with that larger model than with a smaller model. The relative accuracy does like converge though as time goes on, and I don't think this is terribly surprising either. This table here is somewhat interesting. So what they're showing is the performance gaps between this delta t and just normal delta. So let me just see if they have the explanation there. Yeah, so continuous prompts that project to true target prompts are no more effective at solving whatever the end task is. The average performance gap is about the same for continuous prompts that map to true task definitions as like to a relevant text. So this T is the benefit of mapping to a true text versus a random text. And as you can see, these are not all that different. In the case of like Trek, that is actually going to be higher. So definitely an interesting finding here, and suggested that there is definitely some waywardness going on. So fortunately, they have some explanations for this. So I think this explains a lot of this. The mapping between continuous and discrete space is not one-to-one. So that means that there are infinitely many continuous prompts that project back to a fixed discrete target prompt. So it makes sense that, you know, we can sort of be like lost in this projection space for one. And they talk about a little bit how we can have different distance metrics, different means of like projection from the continuous space into the discrete space, and that's going to affect how we actually come to interpret these continuous or discrete prompts. So they get into some propositions here that I think are interesting. I won't get too into this. They mentioned deep models give a lot of expressivity power to the earlier layers, hence prompting matters. Let's see. Yeah, and I think this section is super interesting as well. Happy to discuss more on this. But yeah, the faithful interpretation of continuous prompts is going to be very difficult as a result of this sort of imprecise non-one-to-one mapping. So you can imagine a case in which someone develops like a language model for doing something important. I think they, like assessing applications for a job. To assure their customers, the model designers use the projection of the prompt that expresses a benign definition for the task, which does not reveal the true nature of the egregious behavior. This, in my mind, is super important because we can't actually interpret continuous prompts, and that gets to be a problem. They mention some like values in using, thus like discrete prompts that are like prompt engineered. We don't know how to automatically and efficiently find these discrete prompts. And they sort of raise the question of whether there's a way to use continuous and differentiable optimization on top of autoregressive language models to find human readable prompts. Waywardness poses a challenge to this very important task. So I think that is basically it for this paper. Looking forward to talking more.